Hello everybody, this is the second video associated with chapter 3 of the reinforcement learning course. So in the first part of the video, we've introduced Markov decision processes, and now we will continue discussing these types of frameworks along with providing some definitions and terminology which will be useful in subsequent chapters when tackling reinforcement learning problems. So we saw in the previous video that the typical objective of an agent in a reinforcement learning setting is to find some policy, where a policy is a mapping from the various states to possible actions. So it's to find a policy so as to maximize the expected rewards, the sum of all future discounted expected rewards um, provided by the policy. So, rewards, what are they in practice? For some problems, rewards are clearly given by the problem. Okay, so for example, if you're trying to design a trading algorithm, well, your profits and losses at every day, for instance, or every time you make an action, will represent rewards. Okay, so a reward is in terms of dollars. This has a clear interpretation. But for other problems, it's not so straightforward. Okay, so you have to design the reward to allow your agent to learn what you want him to learn. So, for example, if you have a maze and you want to train a robot to escape the maze as fast as possible, what you could do, for instance, is to give a reward of 1,000 to the robot when he escapes the maze, he or let's say it, and a reward of -1 every time it takes a step. Okay, so this will encourage the robot escaping as fast as possible from the maze because he wants to take as less steps as possible, because every time he takes a steps he gets a negative reward. So he wants to take as few steps as possible before getting the terminal reward of 1,000 when escaping the maze. Okay, so in this case here we can see that this number of 1,000 and -1, they are subjective numbers. Okay, so they're not given by the problem. We have to design them so as to teach the agent what we want to teach. Okay, so it's arbitrary in that case. So we won't discuss very extensively the process of designing rewards in the current course. So in the current course, the rewards will always be given, but it's a good thing to let you know that in practice, sometimes it's not so simple, and you have to give some thought about designing rewards in the problem. So if you have to design rewards, one thing that is very important is that rewards represent the ultimate goal we try to achieve, or the agent should try to achieve. Okay, so the rewards should not try to reflect prior knowledge of the agent uh, on how to achieve that goal. It should really just simply be a reward when the goal is achieved. Okay, so you should not give rewards for achieving sub goals. You should only give rewards when the final goal is attained. Okay, so this might seem abstract, but maybe let's give an example with playing chess, that will make this more concrete. Okay, so what you should do in chess is give, for example, a reward of 1 if you win, and a reward of -1 if you lose. And then for all other states, then give a reward 0. So one could think instead, well, why not giving a reward every time you take an opponent's piece? Okay, so if you take an opponent's piece, you're in a better position, and then it should help you winning. Okay, so this is the last statement is prior, what we referred to earlier as prior knowledge on how to achieve the goal. Okay, so you assume that by taking pieces, this will help you winning the game. Okay, but you shouldn't do that. And the reason is that sometimes, if you do that, the agent might learn to take many pieces, but still lose his game. Okay, so if you reward him for taking pieces, the agent will take a lot of pieces every game, but it doesn't mean it will win because sometimes some moves will involve taking pieces, but will ultimately be self-defeating. Okay, so this is why you should really only give rewards when the final goal is attained, not for intermediary goal, which you think might be good eventually. Okay, so the agent will learn to get to intermediary or goals or sub goals to get to the final goal. So you shouldn't tell him directly you should achieve these sub goals. You should let the agent figure it out himself how to achieve the final goal. Okay, because your sub goals, you might be wrong about them. They might not be as helpful as you think. So this should be up to the agent to learn. Okay, now the discount rate, what should it be in practice? That's a good question. So let's recall that the discount rate gamma is what determines the value as of right now of a reward obtained in the future. Okay, so a reward obtained k steps in the future is worth only gamma to the power k minus 1 times what it'd be worth if it was received immediately. Okay? So, gamma determines the relative importance of rewards received in long term versus rewards received in the short term. Okay, so here we could have extreme cases. So if we take the extreme case that gamma is 0, then your agent is myopic and he only cares about the next reward because all subsequent rewards have a weight of 0. Okay, so the case gamma is equal to 0 and tells that the agent is greedy and wants only large rewards right now and doesn't care about the future. Conversely, if you take gamma is equal to 1, then this is opposite. Rewards far in the future are as valuable as rewards obtained almost immediately. Okay, so the larger gamma is, the more far-sighted the agent is and puts more weight on long-term rewards in comparison to short-term rewards. Okay, so large gamma entails long-term rewards are worth almost as much as short-term rewards. Small gamma means you discount a lot long-term rewards and don't care much about them. Okay, so last time we proposed a goal for the agent in the Markov decision process. So we assumed that the agent wanted to maximize the expected return he will receive. Okay, so he wants to select sequences of actions so as to maximize the expected return, and the time t return was defined as the following. So the time t return is the sum across all future time periods of gamma to the power k, so the discount factor for each period, times each of the rewards obtained in each subsequent period. Okay, so here, can we re-express this gain in a recursive manner? The answer is yes. Okay, so we'll provide a recursive representation of, sometimes I say gain, but I should say returns. So there exists a recursive representation of returns, which will become very handy in subsequent chapters. Okay, but we will present that representation right now. Okay, so the return is the sum of all discounted rewards in the future. So here, this infinite sum, we can break it into two. We can take first the term when k is equal to 0, and then all terms where k is strictly greater than 0. Okay, so when k is equal to 0, gamma disappears, so the reward is RT plus 1. And when we select all other terms, we make the sum start at k is equal to 1, but we can also take one of the gammas in front of the summation, and then we obtain this. Okay, and then to go from here to here, we simply do a change of index. So instead of starting the sum at k is equal to 1, we start it at k is equal to 0, but we increment the indices of each k by 1. Okay, so here instead of being k minus 1 becomes k. Here instead of being k plus 1 becomes k plus 2. And here this guy, do we recognize this quantity here? Well, this guy is the return at time t plus 1. Okay, so it's exactly this formula here where we replace t by t plus 1. So it's the return at time t plus 1. So this gives a recursive way to express returns at time t. Returns at time t is the rt plus 1, so the next period return, reward, sorry, plus the discount factor for a single period times the next period return. So here we had time go to infinity, but this formula also holds when you have a finite termination time. Okay, so when you terminate your experience at time capital T, recall that this termination was defined as the first time you attain some absorbing state. Then the previous formula can also be shown to hold. Okay, you simply have to set g capital T, so the return at time capital T is equal to 0, because after time capital T you don't receive rewards anymore, and then you can still apply this recursive formula to get previous returns from previous steps. Okay, so here, so why g capital T is equal to 0? It's because all subsequent rewards after the termination of your experiment is 0. Okay. So now, in what we did previously, we had that the termination date of the experience was the first date or first time step you reached some absorbing state. Okay, so let's go back a few slides here to see how we define capital T. So here, okay, we called it arrival time. So the arrival time capital T was the first time you arrived at some absorbing state. But this absorbing, the time it takes to go there, it's random. Okay, so you don't know in advance how much time before you get to there. So let's go back to where we were. Okay, so in practice, there are some problems, Markov decision problems or processes, where the time horizon is finite. Okay, so you want the experiment to last exactly, for example, 10 time steps or 10 years, and this capital T must be fixed. Okay, you won't, you will never go beyond that time. Okay, so for example, if you're a portfolio manager, sometimes you want to manage your portfolio with an investment horizon of 10 years, where you occur, let's say you adjust your portfolio every year. So in that case, capital T, it should not be random. It should really be exactly 10 periods. Okay, so this looks like a distinct case from what we've introduced earlier, where capital T, the arrival time, was random. But we're going to see that it's quite simple to reconcile both cases, in fact. Okay, so one thing before we continue, in these problems above where capital T is fixed, you might act differently based on the current value of T, which is the current time step you're in. Okay, so for example, let's say you're investing for your retirement. If you have 30 years left before retirement versus if you have 1 year left, you will have probably very different investment policies. Okay, so you might be much more aggressive when you're young than when you're old in terms of investment. Okay, so because of that, um, we can see that in this case we just described, the optimal action might not depend only on the state in which you're in, but also on the current time step. Okay, so your problem becomes non-homogeneous because you act differently for various time steps. Okay, so this framework looks different from what we had earlier, because earlier we said that only your state can characterize your action, but we will see now that we can reconcile both frameworks quite easily. Okay, so how do we do that? Well, we can define the set of here I referred to them as raw states. So the set of raw states, stylized S, represents all the states of the nature. And then we can define another set, stylized T, which is the set of all time steps. And then for such problems, we can define the set of states as the Cartesian product between stylized T and stylized S. Okay, so a state is in fact the combination of one of the time steps and one of the raw states of the nature. Okay, so for example, for these types of problems with a finite time horizon, not finite but fixed time horizon, then you can define states as the combination of a time point and the raw state, which represents the state of the nature. Okay, so for such problems, transition probabilities are such that it's if you're in a state of the form T S prime, S tilde, the only possible transitions are those who switch to another state of the form T plus 1 S tilde prime. Okay, so here the only possible way to travel from state to state in these types of problems is if the time increases by 1. Okay, so if you're at time t in the last period, you're going to end up at time t plus 1 in the next period. So only these types of transition between states are allowed for these problems. Okay, for the various values of S and L tilde prime being raw states. So in other words, if t prime is different than t plus 1, it's impossible to go from a state which contains time t to a state which is different, where the first component is different than t plus 1. Okay, so you can only progress forward through time in these problems, which is reflected by transition probabilities. And furthermore, in these types of problems, we can define the terminal state S star as the group of all states of the form capital T S tilde for the various S tilde being raw states. Okay, so when the first component of the state becomes capital T, so let's say capital T in the previous example was 10 years, then you reach the terminal state. So this forces you to stop the experiment at that point, and then capital T indeed becomes the arrival time, because this is the time at which you arrive in state S prime. Okay, so having this enforces that your episode goes through states of the following form. So you start in the state 0 S tilde 0, where this is the first raw state you're in, first state of the nature. Then you transition into a state 1 S tilde 1, etc., until you transition into a state capital T S tilde T. So you're sure to go exactly through capital T plus 1 time steps in these types of Markov decision processes. So you indeed have a finite time horizon, and capital T is still defined as the time at which you reach the terminal state. Furthermore, having states defined like this entails that you can easily reflect that you behave differently as time passes because, for example, if you fix S tilde, so let's say S tilde 0 is equal to S tilde 1, you can be in the same raw state into two consecutive steps, but because the state also involves another component, you might have a different action associated with these couples. So here, maybe even though the two S tildes might be the same, you might have a policy which entails taking one action in this state, which is the combination of 0 and S tilde, and another action in state 1 and S tilde. Okay, so this allows you to define policies where you behave differently as time goes by. Okay, so now we've discussed policies a bit loosely in the past, but we will now formalize its definition. Okay, so we will formalize what we call a policy, and then we will provide a definition for what we call a value function. So a policy pi is a mapping from states to probabilities of selecting each possible action. Okay, so here pi is a function, but we denote as pi as the probability of selection A when in state S. So let's say you're in a state S of the nature. Let's say you have 50% probability of taking action 1, 50% probability of taking action 2. Then you would have the following. Maybe let's write it. You would have probability of selecting action 1 given your state is pi to S, which is 50%. Okay, so this tells you that you have 50% chance of taking either action 1 or action 2 if you're in state S currently. Okay? Okay, so here that was the definition of a policy. It's simply a function which takes as an input a state, and then for a given state associates a probability for each possible action. So this leads to the definition of the state value function. So in the K-arm bandits chapter we studied earlier, the value of some action was simply the expected reward associated with this action. Okay, so there was a single state in these problems, so we didn't have to define the value of a state. But now we will define, of course, we are generalizing what we saw in chapter 2. So we will now define what's the value of a state under a given policy. Okay, so the value of a state S under a policy pi, which we denote by V pi S. So here this stands for the value under a policy pi of a state S. It's defined according to the following formula. It's the expected return at a given point in time if you start in state S and follow policy pi. Okay, so value of a state, it's the expected discounted rewards in the future if you start in that state S and you follow the policy pi. So why is it important to have the value of a state depend on pi? Well, it's because first the rewards distribution, they depend both on actions you take and states you're in. Okay, and pi, your policy, determines both actions you take in the various states, but your actions, they also influence states in subsequent periods. Okay, so when you choose different actions, you're likely to end up in different states which are associated to different rewards. Okay, so your rewards distribution in the future, it depends, of course, on your initial state you're in at time t, but they also depend on your policy because this will also influence future states in which you will be in. Okay, so here again, e pi denotes the expectation given that the agent follows the policy pi. And here, let's observe something. T is any time step t. Okay, so here, there's no t here. The value of a state doesn't depend on time t. And the reason is that we assumed earlier time homogeneity in transition probabilities. So we assume that the transition probabilities, they didn't depend on time. They remained the same through time. And for this reason, whatever the current time step is, t, if you start in a state S and you follow some fixed policy, you will your expectation of the future discounted rewards will be the same regardless if you're at time 1, 2, 3, 4, 5, or anything else. Okay, so in this case, if you start in state S, it doesn't matter at which time step you're in, your expected reward in the future will be the same. Okay, so this is sometimes referred to as time homogeneity. Okay, one quick note here. So the value associated with the terminal state S prime, or the absorbing state, it's always 0. Okay, because if you start at some point in state S prime, all future rewards will be 0. So in that case, the value of the terminal state is always 0. So v pi is called the state value function of policy pi. Okay, so v pi is the function which maps a state S into the value of that state. So it's known as the state value function. Okay. Okay, but if we change pi, of course, you have a different value for the various states. So in that case, the state value function depends on the policy pi. Okay. Similarly, we can define another type of value function, which we will call the action value function for a policy pi. Okay, so we define the value of taking action A in state S under some policy pi, which we denote as Q pi SA, as follows. Okay, so Q pi SA is the expected return if we start in state S, if we take action A immediately, and then for all subsequent actions, we follow the policy pi. Okay, so Q pi SA, it entails starting in state S, taking action A right now, and then for all subsequent actions in subsequent states, the action will be determined by your policy pi. Okay, so in theory, pi should also impact your immediate action, but here, when calculating Q pi SA, we're going to assume that we take action A regardless of the policy right now, and then for future steps, only then you will follow pi. So this is represented as the expectation under policy pi of your return at time t, given your current state is S and your current action taken is A. Okay, and we can replace again the return GT by the sum of all discounted rewards. Okay, so this function Q pi here is defined as the action value function for policy pi. Okay, so we've defined state value function, which is v pi, and here the action value function, which is Q pi. So we're going to see later on that in v pi and Q pi, they play a very important role in the optimization of a policy. Okay, so typically, we'll see that later on, but we typically want to find a policy pi which maximizes the value functions, either state value function or action value function. Okay, we want to find policies which give highest expected rewards, so which try to maximize these functions here. In practice, these functions are, of course, unknown. So let's say you play chess, you don't know uh, before doing the reinforcement learning optimization what would be these value functions. So a key function of many reinforcement learning algorithms are to attempt estimating these value functions. Okay, so in practice, these value functions, they can estimated from experience. Okay, so you have some form of trial and error, which is proposed by reinforcement learning, and then from these trials, you can typically estimate these value functions vpi and qpi. So, for instance, one strategy that we will discuss in chapter 5 to estimate v pi s is the following. So let's say we want to estimate v pi s. What we could do, well, we could start the system in state s and then play many episodes starting in that state s and then following your policy pi. Okay, so and for each episode you can observe the various rewards at all steps, so you can calculate the initial returns uh, for each of these episodes, and then if you average all the returns, this would correspond this should converge to the expected return, which is the value of your initial state. Okay, so uh, this is one possible approach. We're going to see many more approaches in subsequent chapters, but an example of an approach to estimate v pi s is simply to play many episodes starting in state s and following policy pi, and then just simply by averaging the returns for all episodes, this should converge eventually to the true expected value of the return in that state, which is v pi. Okay, so you can have a similar type of procedure to estimate q pi sa. So you can have many episodes where you start in state s and then perform action A immediately, and then for all subsequent actions you follow policy pi. So if you do that, again, you can calculate the return for each of the various episodes, average these returns, and this should converge to their expectation, which is q pi sa. Okay, so these type of approaches, we'll study them more extensively in subsequent chapters. So for example, in chapter 5, 6, 7, etc. Okay, but this procedure where you just average returns for many episodes, they're seen in chapter 5 through the label of Monte Carlo methods. Okay. Now we will introduce what we call the Bellman equation for the value function v pi. Okay, so this is a very famous equation, both in reinforcement learning or through of what we're going to call dynamic programming. So here we haven't talked about dynamic programming yet, but we're going to see subsequently that dynamic programming is the foundational theory behind reinforcement learning. Okay, so this is very important, and this Bellman equation, it's probably the single most important equation in dynamic programming. Okay, so this result, it's very important. If you have trouble understanding this, please take some time to reflect on this. Okay, it's very important. So we're going to see a recursive relationship which applies to the value function associated with a policy. Okay, so v pi s, by definition, it's the expected return at some time point t. T, it can be any t. Okay, it can be t is equal to 0, 1, 2, 3, etc. Any generic t will do. So it's your expected return given you start in state s and that you follow policy pi for all subsequent actions you take. So again, we can replace the return here at time t with what we obtained in the recursive relationship obtained a few slides ago. So here, the return at time t is your next period reward plus the discount factor times your next period return. And now we can use the double expectation theorem. Okay, so for those who didn't do an advanced probability course, well, advanced, like if you did stat 349, you should know this thing. Otherwise, I'm gonna tell you here, but you should try to look up this result, maybe on Wikipedia or some other source, because you should be familiar with that. Okay, so this result says that uh, if you have an integrable variable x, then the conditional expectation of, sorry, the unconditional expectation of the conditional, sorry, I'll say that again. Maybe I'll write it here, given G1, where G1 is included in G2. Okay, so here G1 and G2, I won't define them formally. Okay, if you do more advanced courses, you can see their formal definition, which are, and they are called sigma algebras and stuff like that. But let's not go into these advanced details. So here, if x is a random variable, and here G1 is a set of conditions which contains less information than G2. Then we have a result which says that the conditional expectation of the conditional expectation of x given the set of information which has more information, and then given the set of information which has less information, this should be equal to expectation of x given G1. Okay. So if we do that, we can apply this formula. I'll just change color to apply this result to this expectation here. So this expectation, it can shown to be equal to the expectation. I'll drop the subscript pi just to be more simple. So here are t plus 1 plus gamma here here like this, st plus 1 st at here given st. Okay. And this, from the Markov property, this expectation inside is given as the expectation of gt plus 1. Okay, so here, this part here, from the Markov property, once you know the state at time t plus 1, okay, so here, sorry, I used G, but I should have used a different symbol. Okay, so let's call it G bar here. Times, but not times, but given st plus 1. Okay, so we can replace here. So sorry, in fact, we didn't even use this. Oh yeah, we did. No, we didn't. Sorry for that. Did we? Give me 1 second. Yes, we did. Okay, so here, this conditional expectation of gt plus 1 here, we can rewrite it as the expectation given st of the expectation of the return given st, but also at and st plus 1, so given more information. And this guy here is v by st plus 1. Whoops. Sorry. Okay, it's sorry for that. Maybe is equal to vt v pi, sorry, st plus 1. Okay, so doing that, then we have the following. So here we have the expected value of the next reward plus gamma times the expected value of the next return here. And this here, it is the value function in the next state here. Okay, so because of that, we have the following relationship. Okay, so when we, okay, sorry, maybe this was a bit messy, but we can here see this allows giving a bit of context of how to go from here to here. Okay, so here when we calculate this conditional expectation, we start in state S, then what happens next? We have to select an action A as from our policy, so we have to sum across all possible values of A the probability of selecting each respective action, and then once you take an action, you end up in the next state S prime, and you obtain a reward R. So you have to calculate all the possibilities of the next state S prime and the next reward R, and then we calculated the expectation of what the reward R plus gamma times here, as we mentioned, due to the double expectation theorem, this is the expected value of the gain at the next state S prime. So this expression here, it looks very complicated, but it's simply, so let's remove that, remove all the sorry for that, it's a bit long. Okay, so this formula, it looks complicated, but it's simply, so an expectation of x is simply the sum of possible values over, let's say capital X here, a random variable x, sum of values of possible x times the probability associated with this value. Okay, so here it's exactly that. So to take the expectation of the next reward plus the next expected return, then we take all possibilities, so all possibilities of actions, all possibilities of next states, all possibilities of rewards. Okay, so here this gives the weights, kind of this quantity. So here these are the probabilities for all possible scenarios for the next time step times the x here, which is the reward itself, plus gamma times the expected gain, expected return at the next step. Okay, so here how this return becomes an expected return, it's through that double expectation theorem we just outlined. So here, here this unconditional expected return becomes a conditional given the next state, and the next state is denoted by S prime here. Okay, and then as we mentioned, this quantity here is the value function associated with policy pi at the next state S prime. Okay, so this requires a bit of a meditation or reflection. Sorry, I was a bit messy in my notation, but please take some time to convince yourself that this is true, and maybe have a look also at explanations in the book, because they're a good complementary source of information that maybe explained it a bit better than I did. Okay, but this, in a nutshell, this results in the following. We have that the value function for policy pi in a state S can be expressed recursively as the value function for policy pi in all other states S prime, according to this following relationship. Okay, so this is a recursive relationship for the value function that must be satisfied by the value function f pi, which is known as the Bellman equation for v pi. Okay, and here, just an additional detail here. So when we write pi as a bar s times p s prime r s a, okay, so this looks complicated, but it's really the probabilities associated with all possible scenarios for the next time step. Okay, so it's simply the probability of the next state, the next reward, and the next action given the current step. Okay, so this is the probabilities about all possible outcomes that can happen between state S and the next step, where we end in state S prime. Okay, so this relationship, it looks maybe a bit hard to memorize, but we can use the following plot presented in the next step to memorize it. Okay, so, before the plot, a quick comment. The Bellman equation for v pi, okay, so this is recalling what I just said, but the Bellman equation for v pi, it links the value of a state S to values of its successor states. Okay, so here it links the value of a state S to value of all potential states that will be subsequent to the state S. So if we forget about a formula for a minute, we can interpret the Bellman equation as follows. It says that for a given policy pi, the value of a state is a probability weighted average over all possible actions, rewards, and successor states of the current reward plus the discount rate times the value of a successor state. Okay, so in a nutshell, the value of a state here, it's the expected value of the reward you receive at the next time step plus the discount factor times your expected value of the next state. So this says that if your next states have a high value, then the value of your current state should also be high. So if you're likely to fall in states where you have very high value in the next step, it means that right now you're in a good position to end up in these states, and your value should also be high right now. Conversely, if you're likely to end up in states where you have a low value in the next step, it means that you're in a bad situation right now, and the value of your current state should also be low. Okay, so subsequent chapters, they will show how this Bellman equation allows computing and approximating and even learning your function value v pi. Okay, so as we said, v pi in practice, it's unknown. So reinforcement learning problems will provide ways to estimate and learn these value functions. Okay, so to determine what are the values of the various states. Okay, so one last quick detail. The Bellman equation looks very hard to memorize, but this following plot, which we call a backup diagram, they can be helpful to memorize the equation. Okay, so what this backup diagram says, it says that you start in a state S, then from your policy pi, you will take an action A, and then once you've taken an action A, your transition probabilities will determine the probability of all next rewards and all successor states. Okay, so here, when you calculate, so if we go back 2 slides, when you calculate the value of a state S, you have to sum over all possible actions A, successor states S prime, and rewards R. And here, what are so you sum over all these values, but you weight these values across their probabilities of happening. Okay, so the probability of action A happening if you're in state S is pi. So this is why in the diagram you have pi, which drives the probability of the next action A, and then the probability of next state S prime and next reward here is driven by your transition function P. So this is why P characterizes probabilities of all rewards and successor states. Okay, so this diagram shows that to calculate the value of a state S, you need to know all possible actions and know their probabilities given by pi. And then for all possible actions, you have to take into account all subsequent probabilities of rewards and successor states, which are determined by your probability P. Okay, so in a nutshell, the value of a state is a sum of all possible values, a weighted average, okay, where the weights are the respective probabilities of the various scenarios that could happen. And when I say scenario, I mean the next action, the next reward, and the successor state. So it's an average weighted by their probability of happening of the next reward plus the discount factor times the value function at the next state. Okay, so you really need to take a combination of all possible actions, all possible rewards, all possible states, S prime, and then weight all these possible scenarios through their probabilities, which are given by pi, the policy pi for the action, and by the transition probabilities for the next reward and the next state. Okay, so this is what we call the backup diagram, which can help us memorize the Bellman equation. So we will stop at this point, and I'll see you next time for the last part of chapter 3. Have a nice day.